Okay. Hello, everyone. Welcome to Embodied Intelligence Seminar Series. Today, we have with us Felix Wang. He is a final year PhD candidate in electrical engineering and computer science at MIT. He is advised by Professor Julie Shah. His research focuses on adopting pre-trained manipulation policies for human-robot interaction. He has worked with Professor Dieter Fox at NVIDIA Robotics Lab, and he is also the recipient of MIT Presidential Fellowship and the Work of the Future Fellowship in Gen AI at MIT. His research has been recognized with oral and spotlight presentations at Coral and ICLR. His work is also featured on PBS and is currently exhibited at the MIT Museum, which you should check out if you get a chance. So with that, I would pass on the mic to Felix. Welcome.
Thanks, Poke, for the warm introduction. And thanks for everyone for coming. Today, I'm going to talk about Inference-Time policy customization via interactive task specification. I'll explain what I mean by these words, but at the end of the talk, you will see how I can interact with robot the way you're seeing on the screen. When I started my PhD in 2019, Richard Sutton put out the Bitter Lesson article. The high-level idea is we should, instead of thinking hard about algorithms and then building priors into our systems, we should think about how can we do data collection and then model training in a scalable fashion. In particular, he emphasized there are two things that we should still focus on, which is search and the learning. At that time, I didn't quite understand what this is, and I spent most of my time thinking hard about algorithms. So 80% of my time, I think about algorithm, and maybe 20% of the time, I think about data. But then as time goes on, I start to see news articles like people are hiring, companies are hiring people to do data collection, annotation. We see this large-scale knowledge transfer from humans to some digitized form so that machines can learn from these knowledge given by humans. And then I thought, okay, maybe I should really pay attention to, learning from data, especially when I realized a lot of the algorithm I develop, when the assumptions or priors fail to hold, then those algorithms fail to work. So in my second year of the PhD, I spent 80% of the time thinking about data, and then maybe 20% of the time thinking about algorithms. But then I quickly realized there's no way for me to compete with these big companies collecting lots of data with a lot of training power to train big models. So while I remain miserable in my lab, I see this tremendous progress put out by OpenAI and other companies where they see that as you scale model parameters as well as compute and data, you get a better and a better performance. This curve is very encouraging. It works great. But I feel my research is irrelevant because I cannot train these big models until the scaling law start to fade and start to work for these big companies. OpenAI recently, there are news that showing recent evidence showing that as big companies scaling the data and compute, they're reaching diminishing returns. What they're showing currently is a shift from scaling data and training from training time to test time compute, where they show continued performance if you put more emphasis or resources into search from your pre-trained model. So this is what I thought, oh, maybe I can help with this process because now I don't have to work on pre-trained model. I can take the models pre-trained by other people and then figure out how can I get the most juice out of this. So this talk, I'll focus on how can we take pre-trained policies from other people and then make it interactive so that human can take the policy to do things the human intended to do. This data scaling phenomena is also everywhere in robotics. So for example, Tesla is collecting a lot of data using teleoperation on this humanoid. Toyota Research Institute also built this bimanual interface for people to teach robot hard skills. Other institutions has built this other systems like universal manipulation interface to collect data. And then Google has built this Aloha farm, trying to hire more people to collect this dexterous skills. The common recipe behind these data collection regime is you collect lots of motion trajectory data, and then you train a multitask imitation policy. And then at inference time, you roll out these policies autonomously to generate behaviors. But one question I have is, why do we need, what are we using these policies for? Like, why do we spend so much time collecting data, training the policy, and then do autonomous behavior generation? The use case, the downstream use case for training these big policies is for example, human-robot collaboration in manufacturing setting or in assistive settings, where the humans really want to work with the robot policies in close proximity or tell robot how to adapt to the user preferences. So the key question is, how do we specify human preferences at inference time to influence these policies? These policies natively do not have any interface to accept online human input because they're trained only for a with next token prediction. So they're trained to predict behaviors autonomously. So the question I want to ask in my research is, how can we repurpose these policies trained for autonomous behavior generation to accept online user input? Another motivation for my research is, even if the user doesn't want to specify preferences in terms of how to do a task differently, rolling out these policies trained in the lab in the real world can often fail due to distribution shift. In this case, the robot fails to pour that shrimp into the bowl, even though the demonstration tells it to do that exactly. And that's a big, and then when humans see this kind of failures, there is currently no way for humans to mediate immediately. Oftentimes, you need to restart the policy and then try it again until it succeeds. And then even as people are scaling the foundation models for robot policies, we still see, as this policy becomes better and better, we still see gaps at execution time. When I try the policy myself, this gap remains bigger. That is, meaning if you try the policy to pick up something in your lab setting, oftentimes it fails to pick it up. And then I felt I have no way to intervene or provide my corrections during this process. So how can I do that? This is the question that my research is trying to answer. There are ways for humans, for users to incorporate online feedback. One is through language. There are works that show you can use language as a correction mechanism or a task specification. And then for low-level preferences, you can use Sketch to indicate how you want the robot to perform a task. The common thing among these approaches is you need to train a special purpose interaction ahead that take human interaction input and then condition your policy on it. What that means is it requires additional data collection of the labels of your interaction data, so that you can turn a policy that is not conditional interaction into a policy that is conditional interaction data. And that additional training requires additional data. And while this is straightforward, it might become very inconvenient when you're deploying it, because whenever you change a setup or you want to change your interaction modality, you have to recollect data and retrain your model. Especially as these models are becoming larger and larger, retraining them becomes very expensive. And additionally, if you don't have the pre-training data to co-train your test data with, you risk making the pre-trained model forget its skills. So how can we prevent these kind of issues to have an easy way of turning these policy into something that's interactive? To answer that question, I introduced the framework Inference-Time policy customization, which really built on this idea that from the beta lesson, where we we assume that other people, big companies, they're collecting lots of data using their compute to train big policies that are generalist. They're doing the learning part of this paradigm. What we do instead is we take their model as it is without any training, we perform the search. That is, we find the solutions from these generalist policies that will solve my task at hand. And the big hypothesis here is these pre-trained generalist policy, they already have enough skills. You do not need fine-tuning to improve the skills. You just need a way to find the right skill for your task. To make this concrete, let's look at this toy example, where I want to roll out my foundation policy off the shelf without any changes to pick up this blue object. And perhaps the lighting is different. Perhaps the object location is slightly different. So there's distribution shift. And then the policy tries to do the task, but it fails because it misses the alignment. But that skill is not necessarily a bad skill. We don't necessarily need to change it. Perhaps that skill is perfectly fine had the object been in a different location. What that means is the policy knows how to do this task, but it just fails to recognize which task to do or which object in which location to pick up. Let's assume this generalist policy has this diverse skill set it has learned. Each of them might be successful for a different task scenario. What I'm proposing is we want to condition, given a current scene or context, we want to find the skill that achieves that. And this part human can assist with this part. And then we're going to introduce how humans can help do this task specification to find the correct skill. How task specification is currently done. Right now, if you look at all these big policies, they're training on or fine-tuning on this big motion data set collected by lots of institutions. In this data set, what they provide is the demonstration data, a motion trajectory that solve a task for a particular context. This motion demonstrations encode two things. One is what task to solve, which is specification, and the other one is how to solve a task. The specification currently for this trajectory is weakly inferred through an image, a scene image, or a language instruction. For example, in this case, I could say, pick up the blue object. But oftentimes, this language instruction plus this image conditioning can be quite ambiguous if there are many objects in the scene. So, and during training, there's no one telling the robot that for this particular scene, for this particular instruction, this is the particular object I want to grasp. And then these are the constraints I want to make sure the execution obeys. So the policy can learn spurious correlations with potentially background, irrelevant pixel information or lighting information that are not necessarily relevant to task specification. So the core idea is we only want to reuse the skills learned by these foundation policies, and then we want to overwrite the task specification part. Instead of relying on language and image as weak correlation with the task specification, we ask humans to directly specify the task or the object you want the robot to pick up in the workspace, and then use that as the information to retrieve the correct skill. Okay, so how do we do that? So this is an example of what I mean. Here, I'm rolling out a pre-trained policy, and then that color line shows the prediction of that policy. In this kitchen task, there are multiple objects it can manipulate. For example, right now, in that particular state, the robot predicts it wants to pick up the left blue ball. And this policy is not interactive. We're just rolling it out in a fixed way. And let's say at Inference-Time, user intends the robot to pick up actually the right object. So it uses this red sphere right now to go close to that right ball. And then when it clicks on that user interface I'll show later, it can activate the steering. So, by combining a non-interactive policy, the skill in a non-interactive policy, and then user interactions to specify which task to perform, I can retrieve the right skill. And in this case, it corrects the prediction of the policy. Essentially, I'm switching from one skill to the other one that's more closely aligned with user intent at inference time. And then I execute that. So that's the overall framework or overall behaviors we want to achieve. And there are multiple methods we can achieve that. And here is the roadmap of this talk. This talk assumes we have some pre-trained policy that has multimodal behaviors learned, many skills it has learned. And then in contrast to prior work that fine-tune this policy to incorporate online human feedback, we first look at how can we map user interaction into some cost function and use that to bias the sampling from a multimodal policy. We call this framework inference-time steering. Critically, we don't change any weights. This is a training-free method. And the second method we look at is if the task the human intends is multi-step, there are multiple steps, and then each of the steps has some constraints which are critical for task success, then how can humans specify that task with a symbolic discrete plan and use that plan to make a motion policy to ensure the motion policy rollout obeys the discrete symbolic plan and eventually succeed in the task. So we call that framework task and motion imitation. Both frameworks doesn't change any weights of the policy and are only imposing these constraints through human interactions at test time. Okay, let's go into this inference time steering framework. Given a multimodal motion policy, in this case, a kitchen robot that tries to clean your kitchen, for example, here, you can visualize the multimodal behaviors it has learned. It has learned the skill of picking up left ball or right ball or open the microwave. Let's say at test time or inference time, a user intends only the robot to pick up the left ball first. How can we steer this policy to generate that precise behavior? One way of doing that is through random sampling. You just randomly sample from one of the many possible behaviors. However, in this case, you oftentimes end up with behavior that's misaligned with online user intent. Another way is you can ask humans to physically correct the behavior by nudging the end effector. While this can improve alignment with user intent, it can introduce distribution shift through this physical correction, resulting in failure. So how can we find the right trade-off in between? And then to answer that question, let's first look at what are the interaction modalities we're considering in this paper. The first one is we can allow humans to specify a point goal via moving your mouse in a scene image. When you move this point in the scene image, we map that into the 3D space. And then when you click on it, that sphere turns green and then activates steering. So this is the first interaction mechanism we consider. The second interaction mechanism is through providing a sketch input, either through VR or a 2D drawing that gets mapped to a 3D space. We use that to bias the sampling. And the third is the physical correction. We ask human to physically nudge the end effector until the intended behavior is achieved. So these are the three behaviors we consider in the paper, interaction modality we consider in the paper, but the framework is can be flexibly integrated with any other user input online. Okay, now, given these user input that specify point goals or how you want to do a task via trajectories, how do you sample from that generalist policy to achieve the right behavior? The first, apart from random sampling, which is the baseline, we consider output perturbation, meaning we ask users to directly overwrite part of the policy output in the output space. This is just, for example, nudging the end effector of the policy. We use this 2D maze environment to investigate how this performs, where the alignment means whether you can generate trajectory that's similar to a sketch input the user is providing. And then the success of that experiment is whether the output trajectory remains collision free. And then output perturbation is equivalent essentially to use the sketch input from a user to drive the policy in the space. In this case, this policy has learned from a data set of random walks in this maze environment that are all collision free. So it has learned to predict motions that are collision free. But when you impose this output perturbation by using your mouse to drag that agent around, you can see that the agent is reacting or predicting different behaviors. If you adversarially drag it into the collision objects, it will predict collisions. But when you don't drag into the collision area when it's in free space, most of the time it predicts collision-free behavior. So that's an output from diffusion policy. We also tried interacting with other policies such as action chunking transformers. And then you can see that the behavior from this pre-trained policy is not quite robust. Meaning, even if I'm manipulating an agent in collision-free space, oftentimes it can predict collision behavior, as shown in the visualization. So what this comparison says, when we're using output perturbation as a sampling strategy, we want to choose policies that are more robust, so that you don't risk failing your task by introducing this human interaction. The second sampling strategy we consider is post hoc ranking, which is we let this trajectory pre-trained policy output many sample different behaviors from this output policy, and then we compare which one is the closest to a user input. So in this case, you can ask human to draw a trajectory, and then use, for example, L2 distance to select the one that's the closest. This kind of interaction doesn't introduce distribution shift, so all of the samples should still remain in distribution, but you have not so much control over how fine-grained you want the trajectory to align with your user input. And particularly, this works well with multimodal predictions. If a policy only predicts unimodal distribution, then you don't have much leeway to change the behavior. The third kind of sampling strategy you will consider is related to diffusion. Yeah, you have a question. So like this one. So here, output perturbation, we are not we're literally just overwriting the prediction of the policy. There is no classifier guidance. It's, for example, if my robot is going towards the left, and I'm literally pushing it to the right. So we're not doing this sampling strategy is not diffusion specific. It can apply to any base policy. Yes. The sketch input exert influence after the trajectory has been generated. Yeah. Now we consider a diffusion specific steering mechanism where we ask a user to give the sketch input to bias the sampling during the input stage. What that means is you initialize the noise distribution close to the user join, and then do diffusion from that step onward. And then hopefully that can find the skill closer to your input. Because a typical way of doing diffusion to find your skill is you sample from a Gaussian distribution. But now you initialize the initial noise distribution close to your user input, then that has a better chance for you to find the relevant skill. However, this steering mechanism lack control of alignment as the diffusion continues. So maybe later on, the diffusion process might discover behavior that's still very far away from your user input. So how can we actually give user a more fine-grained control over the trajectory generation process? This is when we consider influencing the policy synthesis during the synthesis process. To answer your question, this is the guided diffusion. So a diffusion process take a noise trajectory and then gradually remove noise from it. And then on top of that denoising step, within each denoising step, we're also adding some alignment gradient to the denoising gradient. Meaning as I'm removing noise from my noisy trajectory, I'm also jitter it closer towards the direction that my user intends. So in this case, the influence is happening at every single diffusion step. So user has a better control over the trajectory synthesis process. However, as we're adding the alignment gradient on top of the diffusion gradient, this introduces distribution shift. And you can see the final trajectory from the sampling strategy doesn't quite align with the user input. So the algorithm we introduced in this work is to turn that guided diffusion process into a stochastic sampling process, which I'll explain in a minute. But a high-level idea is you can repeat the diffusion process multiple times. And then just doing that small trick, you can actually sample trajectory with the highest fidelity to your user input. And then in terms of code implementation, it's just 4-line change to your guided diffusion code. So within each diffusion steps, you are adding a sampling step that repeat the diffusion sampling. This helps reduce the distribution shift. And then I'll explain intuitively why this is the case in the next 2 slides. And then if you benchmark all these different sampling strategies with different base policies, pre-trained policy, we observe this trade-off between alignment and success rate. So as we increase the aggressiveness of steering, meaning as we reduce the misalignment, that introduces more and more distribution shift, and then hence the failure rate increases. So this is the thing that we're trying to find a balance between whether we want a trajectory to align closer to user intent or whether we want the policy to behave in a distribution shift-free way. And specifically, if the policy is multimodal, then we have an easy way of increasing alignment without introducing a lot of failure. And if the policy is brutal, then we don't have too much of leeway to increase alignment without increasing the failure. And specifically, our method, stochastic sampling, achieves the best trade-off between alignment and distribution shift. And then to help you understand more intuitively why this works, let's see a video of how it works. So without any human guidance, we just randomly sample from this trajectory. For example, you can see over here that a robot is predicting a trajectory of picking up this left ball. And then let's say the user intend to pick up the right ball. And then it can activate this point input and then use that to correct the behavior. And then the robot continues on and then put the ball in the microwave. Now, the robot is still trying to close that microwave, even though it is already closed. And then the user intends the robot, let's say, pick up a different ball now. So you can use this input to correct the behavior of the policy. And then over here, we see a grasp failure, probably due to distribution shift introduced by this human-robot interaction. But that's okay. We can just ask it to try again. And then again, the robot is trying to put the bowl in the fridge, in the microwave, which is already closed. And then the user wants to correct that behavior. Then we can just change that behavior by interaction. And this whole process is training free. We're just imposing this inference time user intent to find the right skill from this generalist policy. Okay, so how is stochastic sampling different from guided diffusion, and why does it work better? This is a toy example to explain the differences. Let's say our pre-trained policy has learned this distribution shown here. There are multiple modes. Each mode corresponds to a different skill. And then at inference time, a user wants to sample from one of the modes. If the user doesn't give any interaction or task specification, and then we just sample from this, then we randomly sample from one of the modes. But when user do have an objective encoded by this green point here, let's say the user wants to sample a mode that's closest to that green point. And then we derive the alignment gradient and compose them to do guided diffusion. You see that this guided diffusion is effectively sampling from a out of distribution location because it's effectively sampling from the sum of these two distributions. When the user intended goal is not aligned with the pre-trained distribution mode, that introduces distribution shift. But when we're doing stochastic sampling, we're essentially still sampling within a product distribution of the user specified intent and the pre-trained distribution. And this way, we find the skill in the closest mode to user input. So this is why stochastic sampling introduces less distribution shift compared to guided diffusion. Okay. And then to drive home the point, if you use guided diffusion, when you activate the steering, oftentimes you can introduce distribution shift, and then the policy won't be able to find a coherent trajectory. But when you're doing stochastic sampling, you can find the skill in the mode that's closest to your intent. This is how you can steer the policy to generate behavior that's both aligned and within distribution, hence will lead to success execution. Okay. So far, I talked about this inference time steering framework where users can impose their intent at inference time without changing the weights or fine-tuning the model to select different behaviors. But so far, all the behaviors are single step. That is, within a single step of picking something or putting something that I can do that. What if a user wants to specify a longer multi-step plan? That is, for example, if you want to pick up, transport something, you first need to pick it up and then move it over, align your NA factor with target location and drop. What if the user wants to specify this multi-step plan? How do you ensure the motion policy gives you a rollout that aligns with that plan? And this is what I call task and motion imitation. Okay. So how do we enforce task constraints on a pre-trained policy? As I mentioned earlier, this pre-trained policy are only learning to do next token prediction, and they're not trained on explicit constraints. They're only implicitly learning these constraints. How do you explicitly enforce them? Here's a toy example. Let's say the pre-trained policy has learned this motion, valid motion manifold, where sampling within the manifold gives you a valid motion. And for example, this trajectory might give you a successful task execution of scooping some marbles from one ball to the other. But during execution time, a user wants to interact with it, and then let's say perturb the policy. Some of the policy perturbation might not result in failure if the policy is robust. For example, in this case, it can react to the perturbation and still succeed in scooping. But sometimes the perturbation can cause some task level failure, where the robot will drop the marbles. And then from that state on, even if the motion imitation is successful in terms of reaching the target location and perform the behavior, the task is not successful because there's no marbles at the target ball. And then why some perturbation will result in failure but not others? Hence, perturbations are not created equal. The reason for that is underlying all this continuous motion execution, there's a discrete task structure. For example, shown by these intersecting manifolds, where the gray manifold is encapsulating a reaching mode. A blue manifold is capturing the scooping mode, where the boundary encodes the spool needs to be in contact with marbles during successful scooping. And then the yellow manifold encodes the transporting mode, where the boundary again encodes constraints such as you need to ensure your spoon remains level so that it doesn't spill the marbles. And then a trajectory that fails is because it tries to go through these manifolds through invalid discrete transitions. And then valid executions are those trajectories where all the transitions between manifolds are legal. So the task of enforcing these discrete task specification on top of a motion manifold, motion rollout requires two things. The first thing is we need to ensure we have a way of telling which mode you're in or which manifold you are currently on. This is the grounding problem that we need to detect for your current robot state, whether you're reaching or whether you're scooping or whether you're transporting. And after you detect which mode you're in, that is recovering, solving a grounding problem, you need to solve the next problem is how can you then correct policy behavior using this grounding information so that if the spoon drops the marbles, you have a way of getting back on track to rescoop. So I'm going to, for example, here, if the robot detects it has dropped the marbles, it needs to activate a different policy or different skill from the pre-trained policy to rescoop. Okay, let's first quickly look at how do we solve the grounding problem. This is the first step of enforcing this discrete task specification on a pre-trained policy. So given a language plan of mode sequence, for example, for scooping, and then some unsegmented demonstration or motion rollout from your pre-trained policy, can we learn a classifier that can map these continuous states into discrete modes? If we have recovered this grounding classifier, then we can do the following things. We can first recover the boundary. For example, for the scooping mode, you need to keep contact. And then the boundary of this transporting mode, which is to keep your spoon level. And then we can call the relevant policy for each corresponding mode so that you can succeed the task. And a concrete example of the policy classifier you learn is, for example, you can detect whether there are marbles on the spoon at all times. This is a concrete example of the kind of the grounding operator we want to learn. Let's use this 2D navigation task as an example to show how the algorithm works. The task is for the robot trying to go through this color square in this particular ordering. And then if the robot goes to later color blocks without this particular order, then that's a failure. So that's an invalid mode transition, for example, directly going from the white region to red or yellow without first going through green or blue. In order to learn this grounding operator, we need both positive and negative examples of what to learn the constraints. And then to do that, we can add perturbations to a policy rollout, just randomly add noise to the policy rollout. And some of the perturbed trajectory will still be successful because it still obeys all the discrete constraints. But some of the policy rollout might fail because especially if you perturb the policy at critical states where constraint is necessary. And this is an example of how can we add that perturbation to a policy rollout. You just perturb the end effector execution. And then we can generate this trajectory set autonomously without human in the loop, because we can simply code up a reset mechanism. So we collect lots of data where we have successful labels and unsuccessful labels at the end for each trajectory. And let's look at how can we learn this grounding classifier. Given a trajectory and also its label, whether that's a successful execution or not, we can initialize a random classifier and then map that continuous state sequence into discrete mode sequence. This might be wrong. Some of the prediction of the mode sequence might be incorrect, but that's okay. We just randomly sample them. And then we find which of these, we predict whether this trajectory is going to be successful at the end of that, based on this intermediate discrete mode predictions. And then we compare our label at the end of the ground truth label we have collected with the prediction, and then backprop through this entire differentiable pipeline. What that means is we're optimizing the weights in the classifier such that it's more likely to predict the correct discrete mode sequence after each optimization step. So we continue to do that until we achieve a success rate that's high enough for us to be sure that this grounding classifier has learned the correct mapping. And this is an example of that. Like, given this perturbed data set, we can recover this, we can learn a state-based classifier that takes as input where the robot is, and then predict which color state it should be in. And then that matches up with the ground truth shown by the black line relatively accurately. And then we can also learn image-based classifier that takes an image and tell you whether the robot is currently touching a green block or red block. And the reason this is useful is because now we have a mechanism to learn whether there are marbles on the spoon, so that when the robot does drop the marble, it can sort of go back and re-scoop without continuing. So that's grounding affords replanning. And one application of this is you can learn motion policies that are quite robust. For example, given a single demonstration where this blue area shows the in distribution states and all the other parts are out of distribution, you can generalize to all sort of out of distribution perturbation. For example, you can perturb it however you want, even if you land the robot in an out of distribution state, even if it drops the marbles. You can leverage that grounding information to retrieve the skill of going back and re-scoop and until it succeeds. You can prove there is a success guarantee on the system with the correct assumptions. And the next question, the very last bit I want to mention is, now we have recovered the grounding operator. How can we use that information to correct the policy behavior? What do I mean by that? For example, if the robot is perturbed to a state that will lead to failures such as dropping marbles, even though we now have the grounding operator to allow it to replan and re-scoop, but it will make the same mistake if the user perturb it to the same out of distribution state. So this policy, what that means is this pre-trained policy has learned a skill that will always fail at this task. And then the most straightforward way is we can just collect data to fine-tune this policy to make that skill better, right? But what we are doing here is we're introducing a way of modifying that behavior only in the output space without updating the policy weights. Here, for example, if you perturb the robot to that state that's out of distribution and that leads to a failure, we record that failure and then use that failure to inform the policy such that when it perturbs to the same state, it won't make that mistake ever again. So this way, we can use this inference-time human and robot interaction to enforce the constraint and then improve the policy. And then you might wonder, how do we do that? This is the 2D abstraction of that problem, which is you want the robot to reach this yellow goal here within the constraints of this dashed line. All the blue trajectory are successful executions of reaching that yellow goal area without dropping the marbles. And then all the red trajectories are those executions that will actually drop the marbles because they leave this boundary before coming back. So that's equivalent to you drop the marbles and then toe back. Even if you end up in the correct target location, there are no marbles on the spoon anymore. So we want to correct this policy such that all of the behaviors will reach the goal, but also at the same time remain in the constraint set. But the problem is we don't know that boundary because that's not labeled by humans or given to us. So at inference time, how do we reason about that? What we can do is whenever the user causes the pre-trained policy to make a mistake, we can record that failure state and then assume that failure state lives on the boundary of that constraint set. And then if we can make the assumption that each mode is convex, then we can build up this boundary set to inner approximate this convex mode, and then use that as collision boundaries to modify the policy output. This way, we can correct the policy, we can correct the skills learned in the pre-trained policy to adapt to your use case without training the weights, retraining the weights, or changing the weights in your pre-trained policy. And then we tested this out with many human-robot interaction use cases where some humans are trying to be cooperative and some humans are adversarial, trying to stop the robot from scooping marbles. In addition to prove in the paper that the system has a 100% success rate guarantee, we also show empirically it's quite robust to physical interaction correction. And then we deploy them in the MIT museum. And then now that every single visitors can go to MIT museum and they interact with our policy, these are humans, don't know how robots work, so they can be very adversarial. And then, yeah, you can try yourself if you go to MIT museum. Yeah, it's there. Okay, so to wrap up, this second part, I talked about another framework where we allow humans to specify tasks with a longer horizon in the form of a symbolic discrete plan, and then enforce the pre-trained policy adhere to that discrete plan. This way, we can modify the behavior of the policy according to your inference time user intent without changing the weights. So going back to the previous the very first slide, I think my research is trying to bring people's attention, especially our individual researchers like PhD students who don't have the resources to train large models and collect lots of data, to focus on this problem of inference time customization. We can take those pre-trained policy from elsewhere and then make it work for our setups just by thinking harder about how can we do inference time search, and then how can we integrate user specification and inference time to achieve the desired behavior. Okay, so with generalist policy, we can do search. And yeah, with that, I would like to thank all these lovely and great collaborators, and then open up to questions. Yes. Sure.
More about like application time because I know that normally we use the added because
Yeah.
into the grading.
Yeah.
We had the same with
Yeah.
I'm not sure how the other works, but it was similar to
Yes. Yeah, that's a great question. So one of the downside of stochastic sampling is within each diffusion steps, you have to repeat the sampling steps multiple times, right? So essentially, let's say if you want to repeat it, each diffusion step 5 times, then essentially your entire inference time becomes 5 times longer. This indeed is a problem. But what empirically we find is that if we use DDIM as only like if we only use 10 time step for diffusion times diffusion, and then sample 3-4 times, so that can still give us like a 7 hertz real time behavior, and that's fast enough for our use cases. And you don't have to do this sampling step too many times. I think 3-4 times is quite sufficient. Yeah.
Can you go back to one of the slides where you have the Rebecca steering section, like trying to interact with the like?
Yeah, like here.
Yeah, so inside of the, or I think it's a slide where you have like the 3 different inputs.
Yeah.
So inside of this, it looks like essentially what you've been doing is it's providing information about the location where the robot is supposed to be going, but not necessarily anything about what should happen.
Yeah.
I'm curious if you could talk a little bit more about like what that definition of intent is like, because I could imagine, what if you wanted to like flip the bowl or like do something else?
Yes. Yeah, that's right. I think that's a great question. So right now, we only experiment with a discrete goal specification through pointing at something, and then a trajectory shape by sketching something. This is the sort of the granularity we can achieve currently. And then when the policy reaches a state closer to that target, we're sort of relying on what it has learned, the pre-trained policy skills. So we don't have sort of a control over there. But what's interesting is if we can learn a separate classifier that can sort of sort of switch between different behavior modes when it's close to an object. For example, if you have multiple ways of grasping the same object, if you have a way of providing gradient to select which behavior you would like, then you can use that, you can integrate that into my framework. I'm not showing it here, but I think it's compatible with my framework. Essentially, what we're trying to do is we're trying to find different modes of that pre-trained distribution. No, it does not. Yeah. Yeah, that's a great question. Yeah. So here in this framework, a test time, inference time steering framework, if you want to correct behavior, you have to have human, teach the robot how to do it differently every time. That knowledge is not baked in. And I'm working on follow-up, how to bake in that knowledge, but that will require training some weights. But for the second piece of work, where I show you can actually leverage some clever algorithms to only, to learn the correct behavior for only making one mistake. But that's a different framework. So essentially, to your question, there are ways to do that. But currently, this framework cannot, this method cannot achieve that.
I would imagine that you say sketching, you don't know the exact text. So there could be some like discrepancy.
Right. Yeah, that's right. I think that's a great question. So for this kitchen domain, actually, most of the tasks have this sense of discreteness. That is, you don't necessarily want the robot to do random things. You intend the robot to do something that's useful. So that only pick up bowl or open the microwave. So those are distinct locations. So sketch or point input is typically sufficient in this setting. But when you are actually caring about alignment in a continuous motion domain, that's when, drawing something in 2D and map it to 3D will be problematic. And in those cases, we show that you can use a VR to draw that sketch in 3D space and then find trajectory close to that. Yeah, but yeah, otherwise that will be a limitation. Yeah. Yes.
It's maybe a little bit beyond your direction. But basically the question is, you need to understand the model. You need to understand your final models and you want to have variables there.
Yeah.
So you kind of have this standing constraints.
Yeah.
Which, provided from your understanding of the model.
Yeah.
How would you scale up this approach to, not to have to manually drive every particular task? So, we need to have an item to, prime them, and it's the market all basically. We need to have a set of constraints for the steps of when you know how to go and back into the
Yeah. So let me paraphrase your question to make sure I understand it correctly. So you're saying if you are trying to learn constraints for each step, that might not scale very well if you have many steps or have a very complicated task.
But the only way that exists today is just kind of utilize large language models to generate a lot of random constraints out of that. And it's not clear. So what, have any idea how to take care of it?
Yeah, I do believe that a lot of foundation models, even if they show like this model improved performance during training or like in their lab environments, when you deploy them, there's always going to be a gap because during deployment, your environment will always be slightly different. So you cannot just expect zero shot executing your off-the-shelf generalist policy will work. And that gap is where humans come in. And my work is trying to basically say, how can we minimize the effort for humans to correct behaviors? So that human doesn't have to collect a lot of demonstration to fine tune the policy, just with minimal input. It can leverage the most of the pre-trained policy to achieve the desired task. But I do think at least in the next 10 years, there will be a role for humans to play in this execution role. Just like one area where robotics has really shown progress is surgical robots. They don't perform the surgeries autonomously. There's a human surgeon, working with the robot Da Vinci system to execute those skills. So I do think in the next 10 years, at least, there's a role need to be played by humans. And my work is trying to figure out how can I make humans' job easier to control the robot policy. Yeah, thanks.
Speaker.
Thank you. Thank you. Okay, yes.
Again,